We're going to talk here about related rates. So to kind of get the idea of what's going on with the related rates, I have an example here about dropping a pebble into a calm pool of water. And so you can see the ripples kind of move out from where the pebble hit the water. And if you imagine just looking at one of those ripples, you'll see that you've got a circle, and that circle has a radius that is changing with time as that circle grows, that kind of circle formed by the little ridge of the water there. And so since the radius is changing with time, then that means the area of that circle is also changing with time. And so what we get is that our familiar a equals pi r squared really looks like a of t equals pi times r of t squared. That is, we would say, whoops, let me hold that still. So let me get my pen up here. So we would say a of t is equal to pi times r of t squared is what we really mean, but we don't actually usually write that. So we'll still write it as a equals pi r squared, but understand that because the radius is a function of time, then so is the area. And so we would then end up taking the derivative of this with respect to time. And so our variables, our expression would be dA dt. Now, using that Leibniz notation to kind of emphasize that it's the t is the independent variable there, and then the constant pi, and then the 2 times r to the first times dr dt, so it's a chain rule derivative on r squared because that's the function r of t squared. So you get 2 times r to the first times the derivative of the inside function. And so you notice that out of this one expression, a equals pi r squared, we end up with two different derivatives, two rates of changes that are related to each other. So that's hence the name related rates there. So let's see what this looks like in terms of an example. I'm going to try to move this up a little bit. And so in this case, switch my pen to black. So we have a balloon that is the shape of a sphere and it's being blown up. And the volume is increasing at 4, that should be, let's get cubic centimeters. So the volume is changing with cubic centimeters per second. And at what rate is the radius increasing when the radius is 1 centimeter? So we want to kind of make sure we understand what all is going on here. So the volume is increasing, so that's suggesting a change in volume with respect to time. You can see that we have volume measurement in, when I wrote it right, the cubic centimeters, and we also have a time measurement in the per second. So our dV dt is going to be this 4. We're looking for at what rate, so we're looking for a derivative, is the radius increasing. So what we're looking for is a dr dt. And we know also that the radius is 1. So we're looking for at what rate is the radius changing when it is 1 centimeter. Now, the volume of a sphere, you don't have to know this from memory, but the volume of a sphere is 4/3 pi r cubed. So that's the formula we're going to start with. We're going to take the derivative of that volume with respect to time. And so what we're going to get then is dV dt. And then the 3 from the 4/3 pi is just a constant, so it's just going to hang out. Differentiating the r to the third is going to be our chain rule derivative, so we'll get a 3 and then an r to the second, and then times the derivative of the inside function, which is dr dt. We'll plug in all of the things that we know. So we know the dV dt is 4. The 3 and the 4/3 will cancel, so we've got 4 pi. The radius we know is 1, so that's going to be 1 squared, and that's going to let us solve for the dr dt that we're trying to find. So if we divide that 4 pi to the other side, we'll actually get 1 over pi is the rate of change of the radius. Good to keep the units in mind there, and so this is going to be, since it's a change in radius over time, that's going to be in centimeters per second. Okay, let's see if we can go on to that page. So we have some more examples here, a couple more. So now we have that sand is falling off of a conveyor belt into a conical pile at a rate of, and I didn't get the here either, the units there, so that, let's say, is going to be in cubic feet per, and let's say, minute. The diameter of the base of the cone is approximately twice the altitude, and at what rate is the height changing when it is 10 feet high? So we've got a conical pile, so we're going to get something like this. This is our cone, and we're pouring more sand onto the top of that pile. Our formula for volume of a cone, you don't have to know this from memory, is 1/3 pi r squared h. Let's see what other information we know. It's a rate of 15 cubic feet per minute, so that's telling us a change in volume with respect to time is going to be 15. It says the diameter is twice the altitude, so the altitude is the height, and since the diameter is twice the radius, then what that's really telling us is that the radius and the height are equal to each other. We're trying to find at what rate is the height changing, so we are looking for dh dt out of this, and we also know that we want to know what that is at the moment when the height is 10. So, starting with our volume formula here, let's say since we're looking for a dh dt, we want to keep the h's, but we would love to get rid of those r's, and we know that r is the same thing as h, so that means our volume formula is 1/3 pi, then that's going to be h squared times h is h cubed. So we can simplify our volume equation to 1/3 pi h cubed. We can now differentiate this with respect to time, and we'll get a dv dt on the left. We'll get the, I'm going to convert that to a pi over 3. So the 1/3 pi is pi over 3. We'll get 3 times h to the second, and then using our chain rule times the derivative of the inside function, dh dt. So the 3's will cancel, and we're going to get dv dt is equal to pi h squared dh dt. So we can plug in what we know. So the dv dt we said was 15. The h we said was 10. And the dh dt is what we're looking for. So solving for the dh dt, we're going to get 15 over 100 pi. We could reduce that by 5, I guess, and get 3 over 20 pi. And that unit is going to be in feet per minute. Okay? So the third one, a balloon rises at a rate of 8, and I didn't get the units there either, so I'm going to put in here, that's going to be feet per, I don't think I said what that is, let's say feet per second, and from a point on the ground 60 feet from the observer. Find the rate of change of the angle of elevation when the balloon is 25 feet above the ground. So we have this balloon. I think we ought to have a red balloon, and it's going to be what did we say, 60 feet from the observer. So this is going to be our observer over here looking at that balloon. The observer's line of sight is going there. And we want to find the rate of change of the angle of elevation. So here is theta, our angle of elevation. Since we want the rate of change, what we're looking for is d theta dt. That's what we want to find. We know also that the balloon is 25 feet above the ground, so this is going to be 25 feet. And what else do we know? It's rising, so I'm going to call this, let's call this height of the balloon h. So the balloon rises at 8 feet per second. That is a rate of change, is a derivative. So it's a dh dt is equal to 8. So we need some kind of function that we can differentiate. So since we know the 25 and the 60 and our theta is what we have there, that we're looking for the d theta dt, the trig function that connects those is going to be a tangent of theta is equal to the opposite, which is h, because that's changing with time, over the 60 that is not changing with time. So we could maybe call that 60 tangent theta is equal to our h. Now the h is changing with time, that balloon is rising, and that makes the angle change with time also. So our independent variable in all of this is the t. So differentiating that, we'll get the 60, the constant just hangs out. The derivative of tangent is secant squared theta. It's a chain rule derivative because that theta is a function of time. So we'll take that times the derivative of the inside function, d theta dt. And that's where we're going to get what we're trying to find. And on the other side, the derivative of h with respect to t we'll call dh dt. So let's see if we can figure this out. We've got 60. Now we need the secant squared of theta at the moment when the height is 25. So we know that secant is the reciprocal of the cosine. And so secant squared will be 1 over cosine squared. So we need to figure out what is cosine of theta. So let's see, I think what we've got is, since at the moment we're interested in, we have the 25 is the height, the 60 is the adjacent side. So we have opposite side, adjacent side. And so we can either, I just had an idea here, we can either try to solve for the hypotenuse here, maybe call that c, using Pythagorean theorem. We might also try to make it into a tangent. I think there's an identity that we can trade this secant squared in for something with a tangent squared. So if we look at our favorite trig identity, sine squared plus cosine squared equals 1, then if we divide by cosine squared, we'll get tangent squared theta is going to be plus 1 is equal to secant squared theta. So I think we could replace our secant squared theta here by a tangent squared theta plus 1. You don't have to do it this way, but I was trying to avoid doing the Pythagorean theorem with something I don't think is going to work out all that nice. So 60 times, if we call that tangent squared theta plus 1, and then that's still going to be times d theta dt that we're trying to find. And the dh dt we know is the 8. So tangent of theta is going to be opposite over adjacent. So that's going to be 25 over 60 squared plus 1. And then we're going to multiply that in turn by 60. And that's going to be multiplied by d theta dt in order to equal 1. You with me there? I hope so. I'm going to try reducing this 25 over 60. 5 goes into there 5 times, into there 12 times. So that looks like it's going to be 25 over 144 plus the 1, which is 144 over 144, waiting to get multiplied by 60, multiplying the d theta dt equal to the 8. Whew. Let's see, I think that's 169 over 144 times 60. Who made up this problem anyway? D theta dt is equal to 8. Let's see, what can we do there? We know that 4 goes into 60, how many times? 15, I think. And we know that 4 goes into 144, since that's 12 times 12. Canceling the 4 with one of the 12s would make that 12 times 3 is 36. 3 goes into here 5 times, into here 12 times. Let's see, so I think we've about hit the end of the road there. I didn't really want to do this, but it looks like we have 5 times 169 over 12 times d theta dt is equal to 8. So solving for d theta dt, yuck, is going to be 8 times the reciprocal here, which will be 12 over 5 times 169. I'm not seeing anything that's going to cancel there, so I'm going to leave it there for you to put into your calculator. Okay? And I think that's all we got on this one. Okay.